that today. Make a new page here. Let's see. Okay. Okay, so when we first start talking about formulas for derivatives, our variables always agree. And what I mean by that is, for example, you might be asked to find, oops, that's a little thick here, hold on. You might be asked to find the derivative with respect to x of the function 2x cubed plus 4x plus 1. Okay, and we learned the power rule, and we learned how to take derivatives of x being multiplied by a coefficient. But what we kind of gloss over, maybe, is that this variable x that we're taking the derivative with respect to is the same variable here and here. So in this case, it would be 6, because it's 2 times, and then the derivative of x cubed is 3x squared. So 2 times, well, let me just write it out. So it's going to be 2 times 3x squared plus the derivative of 4x is just 4 plus the derivative of 1 is 0. So that means that we get 6x squared plus 4. But the reason that implicit differentiation is going to turn out to be different is because we're going to be, and I'll explain what implicit differentiation is in a minute, but in the process of doing implicit differentiation, we're going to have to take the derivative when the variables don't agree. So for example, if we have to take the derivative with respect to x of something with y's in it, like maybe the derivative of y cubed, okay, this becomes essentially a chain rule problem, because remember, when we take the derivative of something other than x to a power, what do we have to do? We still bring the power out front, and we still subtract 1 from the power, but we then multiply by the derivative of whatever was inside the exponentiation. So in this case, the derivative, we don't know what it is, but we can just say, well, it's the derivative of y with respect to x. So the derivative of y cubed with respect to x is 3y squared times the derivative of y with respect to x. So what it comes down to is when you have a variable other than x in here, you got to throw in that dy dx. It's really the chain rule being applied. Let's look at an example where we have both an x and a y in it. So what if I had to take the derivative with respect to x of the product, oh, that's a little messy, x times y squared. Okay, so these are two different functions. X is being multiplied times y squared, so we're going to have to use the product rule. But we also note that the y is not the y squared function, I should say, the y squared does not have the same variable as we're differentiating with respect to. So first of all, recall your product rule. So we're going to have the first function times the derivative of the second plus the second function times the derivative of the first. So the first function is x. Now, how do we take the derivative of y squared with respect to x? We're going to use the chain rule. So we're going to take the derivative as if we were differentiating with respect to y. So we would get 2y to the first. But since that wasn't an x, we get dy dx. Okay, plus, so this was our first function, and this was the derivative of our second function. Now we're going to write down our second function, y squared, times the derivative of our first function. Now, what's the derivative of x? It's just 1. But I want to point out something. The derivative of x with respect to x would give you this expression, dx dx, which is just 1. So there's a reason why we were not writing when it's an x, when it matches up, we don't end up having to write this little funny looking expression with the d's, because it actually kind of cancels out. So here we have x, well actually let's do 2xy dy dx plus y squared. And that's the derivative of xy squared with respect to x. All right, so the purpose of this little introduction where I showed you how to take the derivative when the variables don't match up is to achieve the goal of being able to do implicit differentiation. So what is implicit differentiation? Let's take a look. Oops. Accidentally opened something here. Okay. Close that. And I'm just going to check on my stream here. All right. Looks like it's recording. All right. Okay. So what is implicit differentiation? Well, implicit differentiation is when we're given something like, for example, the equation y cubed plus y squared minus 5y minus x squared equals -4. And we're asked to find dy dx. So the problem here is that we normally found dy dx by getting y by itself in the function, but there's no way to get y by itself in this function. So in fact, this is probably a relation rather than a function, right? So what we're going to have to do is take the derivative of both sides with respect to x, and then this is going to create a new equation containing the variable dy dx, which we'll then try to solve for that. So here's what I mean. We're going to take the derivative of both sides. So if these two sides of the equation are equal, then that must mean their derivatives are equal, right? So the derivative of the left should equal the derivative of the right. And on the left, then, we're going to have to differentiate this polynomial, which has some y's in it that the variable doesn't match up. So we're going to have to take the derivative of y cubed plus the derivative of y squared minus the derivative of 5y minus the derivative of x squared. And on the right, the derivative of -4, a constant, is just 0. Okay, so on the left, let's look at each one of these. Remember, thinking of it as a chain rule, we're going to bring the power out front of the y, so that's 3 times y, subtract 1 from the power, and multiply times the derivative of the base, dy dx. Plus, here we have the same situation. We bring the 2 out front, subtract 1 from it, and multiply times dy dx. Minus, here we have the derivative with respect to x of 5y. So that's just going to be 5 times dy dx, the derivative of y. And minus, and here the variables match up, so we just have 2x. We could write dx dx, but it's not necessary. That's why we never mentioned it before when we were learning derivatives. We just left it off. Equals 0. Okay, so now what we have is this new equation, and the variable we're looking for is this dy dx. So it's like solving a formula for a particular variable. Okay, let me check on my chat here. It seems like somebody's joined, so if you want, you can post your name. If you're one of my students, you can post your name or alias to get bonus points. Let me know if you are having any trouble seeing or hearing me, or if you have any questions. You can type them into the chat bar. Okay, so let's talk about how we would solve this formula for the variable dy dx. So whenever you solve a formula, let's go off to the side here and look at an example. You may have worked a similar problem back in algebra. Let's say that you had to solve ax plus ay equals c for a. Okay, so solving a formula for a particular variable, one of the tricks that we use is if we have more than one term that contains the variable, we factor that variable we're looking for out. So we'd have a times x plus y, for example, here. And the purpose of that is now we can just divide by the x plus y. So that would be a equals c over x plus y. Okay, so in this simpler example, the variable was a. In our example, our variable is dy dx. But see how dy dx appears in multiple terms? So we're going to factor that dy dx out. So factoring out dy dx, we're left with 3y squared plus 2y, and that's a y to the first, not a prime, minus 5, minus 2x. Actually, let's go ahead and add the 2x over to the other side, so we get equals 2x. Okay? And so now we know that dividing by this polynomial, dy dx of our derivative, our slope of this relation, is going to be 2x over 3y squared plus 2y minus 5. So this gives us a formula for the slope at any pair of coordinates that was on this original equation in two variables. So that's what implicit differentiation means. I'm just checking on, oh, we lost the one person. Okay, I'll continue for those who are watching, who are going to watch the recording later. All right. All right, let's use this technique with a function or a relation actually that you're probably familiar with. So we can kind of visualize the slopes and see how it works out. Okay, so let's find the slope of the tangent line to the graph of the relation x squared plus 4y squared equals 4. Okay, and we're going to find that slope at the point. Actually, let's do points more than one. We have 1 point is the square root of 2 comma -1 over the square root of 2. And another point to 0. Okay, now you may or may not recognize that this is actually the equation of an ellipse. So you might see it better if we divided through by 4 to get a 1 on the right. We would have x squared over 2 plus y squared over 1 equals 1. And this would indicate the lengths of our major and minor axes. And so what we would get is an ellipse centered at 0, 0, which goes through the points oops, I think I wrote this one wrong. This is actually square root of 2, 0. Goes through the points square root of 2. Oh no, that was right. I made an error here. Hold on. Should have been a 4. So that was 2, 0. Oops, that I want us to look at. Okay, so it goes through the point 2, 0. Goes through the point -2, 0. And goes through the point 0, 1 and 0, -1. Okay, so that's what it looks like. Now the points where I'm interested in finding the tangent line. This is actually going to be in my way. Let me move that. The slopes of the tangent line I'm interested in are at 2, 0, which is over here, and at square root of 2, -1 over the square root of 2, which is going to have a slope kind of like that. Okay, so we're going to use implicit differentiation to get a formula for the slope and then plug in these x and y values to find the actual value of the slope of the tangent line at that point. So starting with finding dy dx, we have to differentiate both sides of this equation with respect to x. Okay, and so on the left here, the derivative with respect to x of x squared is just going to be 2x. Now the derivative with respect to x of 4y squared, the variables don't match up, so we're going to have 4 times the derivative of y squared is going to be 2y to the first, or just 2y, times dy dx, the derivative of y with respect to x. And then on the right we have 0. So we have 2x plus 8y dy dx equals 0. Subtracting 2x, we get 8y dy dx equals negative 2x. And then we're going to divide by 8y to see that dy dx, the formula for the slope of the function's tangent line at any point, is negative 2x over 8y. It's not a function, actually. It's a relation. But in any case, so what would then be the slope at 2, 0? Well, since this is an ellipse and we're at the end point of the major axis here, we would expect it to be a vertical tangent line, so we should get undefined, right? So at the point 2, 0, what are we looking at? Dy dx evaluated at positive 2, 0. We're going to plug into the formula negative 2x over 8y, and that's going to give us negative 2 times 2 over 8 times 0, which is undefined. That makes sense, right? Because the slope of a vertical tangent line would be undefined. Now, how about the slope here at square root of 2, comma, negative 1 over the square root of 2? That looks like it's going to be a positive slope of some sort. Let's see how it turns out. Oops, I went a little too far. Okay. So we're going to have dy dx evaluated at, square root of 2, comma, negative 1 over the square root of 2. And so what we're going to do is plug in negative 2 times the square root of 2 over, then we're going to have 8 times y, which is negative 1 over the square root of 2. Okay, so that's going to be negative 2 square root of 2 over, we're going to have negative 8 over the square root of 2. And we're going to invert and multiply, or keep, change, flip, however you like to say it. Negative 2 root 2 times root 2 over negative 8. That's going to be 2 times 2, or 4, positive, over 8, or a slope of positive 1/2. And that looks about right, yes? Looks at that sloping line, that positive slope to the line. It's kind of a gradually rising line, so it's a fraction, so that makes sense. So that's what implicit differentiation is about. And since there's no one to ask questions today, I'm going to stop there.